Let's talk a little bit about strain gauges, which are used to measure strain. They're used to measure the amount of stretching, basically, that occurs in a material. So they measure strain by measuring resistance. They're basically just these little foil transducers or plastic transducers with traces printed on them. And what they do is they measure resistance, and as the plastic is stretched, the traces are stretched and the resistance changes. So these things can be used for measuring force, acceleration, pressure. There's all kinds of mechanisms you can attach these to for measuring various things. They're very sensitive, which is handy. They're sensitive to really small amounts of strain, on the order of about a micro strain or so, a millionth of an inch per inch of change in dimension. Now, of course, what you're trying to do is you're trying to measure how much an actual part is stretching. So these have to be not just glued down, they have to be epoxied down. The surface has to be prepared very carefully to make sure you have a very good bond between the material, the plastic that the strain gauge is made from, and the part you're trying to measure. So these can measure relatively high strains. 40,000 microstrain is not unreasonable. Now so the way it's made is it's either printed or it's photo etched, essentially, to make the pattern, and was invented by Simmons, and I believe you pronounce it Rue, but I'm not sure. So what happens when you stretch the plastic, and therefore the wires that are on that plastic, is because of Poisson's ratio, this cross-sectional area decreases, right? Because since the wire gets longer, it has to reduce its cross-sectional size. That reduces the cross-sectional area, which is what increases the resistance. Now we will assume a linear relationship between the change in resistance of this resistor and the strain. And the change in resistance, in the first place, these are made to be very precise resistors, but the resistance change can be measured very accurately. So that's how we get to measure very small strains. Now these are designed for high sensitivity only in one direction, because if you look at the way they're printed or laid out, most of the time it's just wires that go along and make a 180-degree turn, come back over and over and over. And so the effective resistance is just the sum of the resistances of all those lines, and so those lines or those rows multiply the sensitivity of the gauge, and as you stretch the gauge, it's like you have a really long wire that you're stretching quite a longer distance, and that's what makes these things so much more sensitive, is because really you have multiple resistors in series with one another. There are two common resistances that are used. There's 120 ohm and 350 ohm. Those are the two most common commercial gauge resistances. That's just the nominal or default resistance. Here's a simple linear gauge, and you can see the pattern. Now notice the 180-degree bends are very thick, so that the resistance in the bends don't change much, but the lines, the rows, are very, very thin traces, and so they're more sensitive to strain along the length of this. Now these are usually very small things, quarter of an inch wide or so by about 3/8 of an inch long, and you can get them in all kinds of sizes. You can also get multiple different designs of strain gauges. This is just one. This is just a linear gauge. And of course there's some pads there for soldering wires too, so you can measure the resistance of the thing. There's also there's many different types, but a really common other type is the 45-degree rosette, or also called a rectangular rosette. And here you've actually got three linear strain gauges just all laid out at 45-degree angles to one another. Now it turns out that if you bond this to a shape and you stress that shape, because of measuring the strain in three directions, there's actually equations, which I've got another video by another professor on main campus that'll show you the equations and how you transform that into two strains at any angle you want, and also shear strain. There are strain gauges for measuring shear strain, but this is a really easy, common way to get shear strain, not directly, but indirectly. Here's some photos of strain gauges applied to several different machines, actually from Professor Du's experience. As I've said before, he worked on relatively larger machines. My experience is in relatively smaller machines. But you can see some Rosette strain gauges that are attached to various areas. Now, the way this works, this is a vibrating assembly where the parts, whatever they be, actually rotate up the spiral due to the vibration energy being added. So this is, I think it's called a shaker conveyor. Several different terms for this. A vibratory conveyor is the term that I've heard most often. But this is where the strain gauges are located on the plates, and they're trying to measure the strain on those plates to make sure they won't fail from all the vibration. Here's another example where we've got a fairly complicated, it's a round assembly that's bolted down. It's got reinforcement pipes, possibly pressurized. I don't know for sure if it's pressurized, but that is pipe thread, so it could be. It looks like the welding is pretty good, so it looks like it's probably sealed. And you'll notice that there are strain gauges in multiple different locations trying to measure how much the material stretches in different portions of the assembly. Now understand, all these strain gauges are applied to points. These are small areas by comparison to the overall area of the machine. And so these are essentially point measurements of strain. You can see another example with another machine where strain gauges are being used on several different of the vertical members, the plates, the reinforcing plates that are horizontal, and so forth. Here's another view of another vibratory conveyor. You can see the shakers on the top. They're pretty serious machines, and so you imagine that as this thing vibrates, it could vibrate itself to pieces. And so you'd like to measure how much the material stretches as it's vibrating. And so you notice 3 more Rosette strain gauges in this close-up here, measuring on the weld, in the general surface, and then in the deformed area of the material as well. You can't really mention strain gauges without mentioning really I should have included another big name in here. Omega is a big supplier of strain gauges, but so is Micro Measurements Group. And they're actually a part of Vishay, I think it's Vishay Precision Group, which was well known at first just for their strain gauges primarily, and then all the peripheral accessories and things that go with it. They're also actually known for photoelasticity. So if you do anything with strain, you will probably order products from these people. They sell through DigiKey. It's a large company, but they're experts. They know exactly how to help you. They can make custom strain gauges for custom transducers. Just a very wide range of knowledge and products available. So whenever you start to use these, you'll encounter this name pretty quickly, so I thought it was worth mentioning them. But you can see a range of some of their products. They're involved in education about strain. They've got applications engineers who are experts. They can help you with whatever problems you may have.